All right, this starts Chapter 10 of Mathematical Modeling and how to set up differential. So if we do not know the functions modeling quantities behavior, but we have information about the rate of change, again our derivative of our quantity, then we could actually set up a differential equation. So for example, we may use the rate of change of a population to then predict the population. So what we want to do in this section is develop a differential equation from a verbal description, word problems, of rules governing the rate of change of a quantity, and then be able to come back and use this differential equation to predict future values. So let's say, for example, a fish population increases at a rate of 20% per year. Fish are caught by fishermen at a rate of 10 million fish per year. How does the fish population change over time? So we're given words that we can now put together and make a differential equation. We can do this by my rate of change. My differential equation is going to equal the rate of increase minus the rate of decrease. My rate of change is how my population, my total population. My rate of increase would be reproduction. And then my rate of decrease would be actually fishing. So let's let P be the number of fish. That's our population in millions. Let time equal time, let T equal time. So the change in the population over the change in is actual our differential equation. The change in population over the change. Well, the information that's give to us is the rate of increase, the 20% times the current population, and then minus what's being removed by harvesting, the 10 million fish per year. So this is a differential equation. What this does is this models how the fish population is actually changing. So as you can see, what's unknown in this equation would be the population. So you could plug in any value at any certain time of the population and then figure out your rate, the change in population over the change in. Another example, so a quantity of a drug in the body. A patient undergoing major surgery is given an antibiotic intravenously at a rate of 85 milligrams per hour. So that's going in. The rate the drug is excreted going out is proportional to the amount that's already in there, present, with the proportionality constant equal to 0.1 if time is. In other words, we're just saying 10% of the drug is excreted per hour. Write a differential equation describing how quantity of the drug in the patient's body changes over time. So again, we have our rate of change of the amount of drug is going to equal the rate in minus. Let Q equal the quantity of drug in the patient's body. In this case, they give us milligram, and T time. And so the change in the quantity of the drug over the change in time is what's going in, the rate in, which they give us, and then the rate out, and this was proportional with how much quantity was already in there. So this is decreasing at a rate of 0.1 times the quantity present at that particular. Let's look at an exponential population. It says population of San Antonio is currently growing at a rate of about 2% per year. Let P equal the number of people in San Antonio, the population, and T time. So the change in the population over the change in time would just simply be 2% times whatever the current population is. So of course what will happen as time goes. Well, if we just plug in different values, of course if there's no population, then there's no rate of change, there's no growth. You can see the growth starts, but then it starts to actually slow down because if you remember, we talked about this of carrying capacity. So as we can see in the beginning, it's very exponential, but as we get further out, we're going to start to see it slow down. A logistic population growth rate slows down when the population gets large enough. So that's what I was implying on the Because, and the reason why is the environment can only support a certain number of individuals, and this, as we've already talked about, is called the carrying capacity. So let's let P equal the population of San Antonio, T time in years. Let this K equal the carrying capacity of San Antonio, and R equals the growth rate of the population of San Antonio when the population is small. So the growth rate R would change as the population size changes. So again, if my population, I'm taking my population divided by capacity, if my population is small, in other words, very, very small, approximately 0, then that piece would go away. We would just have 1. R times 1 is simply R. So the growth rate would be solid. It wouldn't be changing. But if the population is large, meaning that, let's say, I'm getting very, very close to my carrying capacity, then if these are equal, approximately equal, this would equal 1. 1 minus 1 is 0. 0 times the growth rate. So as we can see, as this gets closer and closer to my carrying capacity, this value, my rate, is getting closer and closer to 0. I mean, it never hits 0. There will always be some kind of growth, but it's getting smaller and smaller and smaller as my population gets larger. So the rate of change of population is growth rate, percent per year, times the size. So the change in the population over the change in time is the growth rate times the population. So suppose for San Antonio, once again, we look at 0.02% per year, and this is our carrying capacity of 2 million. So we plug in the values to be able to get our formula for the change in population over change in time, once again, our differential equation. Again, what will happen as time goes on, that if we plug in 0, then of course there's no change, but we're going to start to see, as we're getting closer and closer to that carrying capacity, our rate of change actually slowing down. So this Euler's method is what we use to predict values using different differential equations. In other words, you know a current value, you can calculate the rate of change at that current value, and then you can predict a little bit into the future. If you remember, we did this already. We called it tangent line approximation. So if I have my population, change in population over change in time, then if my initial value, if this is the initial number of people in San Antonio in 2010, I can certainly find the growth rate by using my differential equation. My differential equation, I simply take the rate times the population, and this gives me the change in population per year. So if I wanted to predict the next year, because it would be close enough that I'd probably get a pretty good idea, then I take the current population plus the change, my rate, times the number of years. And then of course this would give me a prediction for within 1 year. So if I write this out, this is what you just saw me do. And then in the general format, this is saying this is where my starting point was 2010. I want to predict 2011. How can I do that? I can take 2010 plus my derivative, what I used my differential equation for, and then times the change. So if you have an initial value of y at t equals a, and you know your rate of change, then you can predict any future values. And this is exactly what we saw with the tangent line approximation, that I can predict this value by taking a previous value plus the rate of change times, and we call this the step size, where you saw me multiplying by 1 because we only had a step size of 1 year. So going back to this example then, if I have my differential equation, which is my rate of change, which was given to me, I can certainly make predictions based off of an original. This gives me my original population. I found this value by taking my rate of change times the population, so that was my rate of change per year, and then times 1 year to be able to do So now I can use this 2011 and I can say, well, 2011 was predicted. All I did was just turn these around by taking previous. I could use 2011 to then predict 2012. So how would I predict 2012? I would take the population at 2011 plus the change at 2011 times, in this case, from just the previous year, 2011 to 2012 with 1 year. And so I plug in these values, meaning this is what I got above when I did my prediction. And then this, of course, is my new rate of change because I'm basing it on my 2011 population. And then my step size is just 1 year, and I get my population prediction. And so as you can see, if we're predicting very, very close values, it looks linear, meaning if I zoom way in, and that's why we call this a tangent line approximation, because we're just looking at these points very, very close within this area. So once I get a prediction method, I could say, well, why would I go from 2010 to 2012 by going through 2011? Why not just change my step size to 2? Meaning that now what I'd want to do is I'd take my 2010, I'd still find my change, but now I'd say, well, I want to know 2012 what's going on, so my step size changes to 2 years, and I get my. So in other words, 2012 can be found by taking 2010 plus the rate of change of 2010 times 2 for. So as you can see, if I jump by a step size of 2, you can see there's a little bit of difference here, okay? I mean, 1,000 people, but the key here is your prediction when you're jumping more than one step size is probably not a good way to predict, because the reason what's going to happen is you might actually see you might get a change here. You're going to see that the rate's changing based on just the previous year. Or in this case, with the step size of 2, we're saying the rate of change didn't change within 2 years. Issue with having large step sizes, meaning if you have 2010 and you want to predict 2020, it's probably not a good idea to do it within a 20-year jump.